This is section 1.1, day number 2, review of functions, secant lines and the difference quotient, as well as symmetry and even-odd functions. So secant lines and the difference quotient. A line through any 2 points on a curve is called a secant line. The slope of the secant line through these 2 points is given by the following. M subscript secant, right, is just the slope of the secant line, which is change in y over change in x. There's 2 main ways that we express this slope formula. The first one, we're going to go ahead and plot 2 points. Let's call this P and Q. I'll go ahead and plot these. So here we have the points P and Q with inputs of x, comma, f of x, and x plus h, comma, f of x plus h. Now this distance right here represents h, right, that change there. So when finding the slope of the secant line that connects these two, we're going to take y2 minus y1 over x2. That should have been blue. x2 minus x1. And what we end up getting is that the slope of the secant line is equal to f of x plus h minus f of x all over h. That right there is called the difference quotient. The difference quotient, or this slope of the secant line, in this form is interpreted as the average rate of change of f over the interval x to x plus h. Our alternate form for the difference quotient, or the slope of the secant line, is using this idea of P and Q being represented by a comma f of a and x comma f of x. So the slope of the secant line in this form would be y2 minus y1 over x2 minus x1, which of course we can't simplify. And the slope of the secant line in this form is also interpreted as the average rate of change of f, but now over this interval of a to x. So let's look at an example of finding the slope of the secant line for f of x equals x squared over this interval from 2 to 3. Let's use this idea of a and x in our second form of the difference quotient. So the slope of the secant line will be f, or y2 minus y1 over x2 minus x1, right? Or this exact form right here, using 2 and 3 and f of 2 and f of 3. Of course, 3 squared is 9, 2 squared is 4, and 3 minus 2 is 1. So the slope of our secant line here is going to be 5. Okay, let's move on to our next slide. All right, let's simplify the difference quotient for f of x equals x squared. So if I do f of x plus h, that means I'm going to plug in x plus h into our function, minus f of x all over h. So our first expression will result in foiling, in which we will get this. Okay, and then we can do some simplifying. We'd see that x squared minus x squared is gone, and you'll also see that there's an h in each of these terms. So it looks like our difference quotient would come out to be 2x plus h. That's what our difference quotient simplifies out to be. So let's find the slope of the secant line for f of x equals x squared over this interval 2 to 3 using the difference quotient from example 2. Okay, compare your results with example 1. So for example 1 we got 5, I believe. So now let's consider this x comma x plus h, right? So our difference quotient is good on that interval. So we're going to say that x equals 2 and x plus h equals 3. So if x equals 2 and x plus h equals 3, we're going to use this, and we're also going to plug it in here and find out that h equals 1. Therefore, when I get my simplified difference quotient, the slope of my secant line should equal 2x plus h, where x is 2 and h is 1. It looks like we've confirmed that both come out to be 5. Alright, let's simplify the difference quotient using the second form, f of x minus f of a over x minus a, for f of x equals square root of x squared plus 1. So let's do this, x squared plus 1, so that's f of x minus f of a, which is a squared plus 1, all over x minus a. So I do want to write this here. The slope of the secant line will be the following. Now a method commonly used when you see radicals like this is to multiply top and the bottom by the conjugate of wherever you're seeing the radicals. So I'm going to go x squared plus 1 plus the square root of a squared plus 1. Same thing on the bottom. Square root of x squared plus 1 plus the square root of a squared plus 1. So we've got conjugates in the numerator, and what's nice about conjugates is that when you multiply them, right, we're going to FOIL, but really we're just going to FL because the outside and inside will cancel. So the slope of the secant line will be square root of x squared plus 1 times itself, which will be x squared plus 1, minus the square root of a squared plus 1 times itself, which would be a squared plus 1. Denominator, no change. Okay, and square root of x squared plus 1 plus square root of a squared plus 1. And what we'll see here is that the 1's cancel. And what actually happens is this numerator, which is now x squared minus a squared, turns into x minus a and x plus a. And conveniently, x minus a is cancel. So the slope of the secant line is represented by x plus a over the square root of x squared plus 1 plus the square root of a squared plus 1. Okay, on this slide here, let's review even-odd functions. So even functions, like the function f of x equals x squared, and odd functions, like the function g of x equals sine x, right, show the following properties. So even functions are symmetric with respect to the y-axis. What that means is you'll see f of 2 is also equal, the output is equal to f of negative 2. What that means is if a function is even, then f of negative x is equal to f of x. Right, like we see in our drawing here, f of negative 2 has the same output value as f of 2. And an odd function, the opposite, well, almost the opposite, similar but yet different. G of negative x is equal to the opposite of g of x. So g of pi over 2 is 1, g of negative pi over 2 is negative 1. G of negative pi over 2 is equal to negative g of pi over 2. So there's an origin symmetry there, rotational symmetry in those odd functions. And one of the specific points in an odd function is that this must be, the origin must be a point on every odd function. So determine whether f of x equals x to the fourth is even, odd, or neither. Well, it's pretty easy. What I do is I determine, is this equal to this? Well, I know what f of x is. It's x to the fourth. So what would negative x to the fourth be? Well, it'd be x to the fourth. Therefore, that would be even. All right, that checks. Let's check this one. I'm going to do my work on the side. Okay, so clearly these are not equal. So our next step is to check, are they odd? Right? So what I want to know is f of negative x equal to negative f of x? Right, so f of negative x equals negative x cubed over x squared minus 1. Would that be equal to negative f of x? And the answer to that, as we analyze it, is yes. You can see that those two expressions would be the same. Therefore, this would be an odd function. All right, let's look at one more here. You're probably anticipating, well, it's going to be neither. I'm going to do the work on the side, and then we can come back and look at it. Okay, so I've analyzed f of negative x equal to f of x to see, is it even? One thing that I neglected on the last example that I shouldn't have, right, I've highlighted that I get a plus sign here in front of the x cubed to show that they're not equal. I have to say that it's not even. So after I've determined it's not even, then I'm going to go on and just work through whether or not it's odd. Okay, clearly my work shown here to see if it's odd does not show equality here. So I can determine it is not odd. It is not odd. Therefore, it's neither. All right, so check even first, then odd. And if it's not odd, then it's neither. All right, let's look at the last couple of examples here. Assuming that f is even and g is odd, right, let's determine g of f of negative 2. Now, one thing that I like to do is I like to think of odd functions. I like to just kind of go on the other side of this table to negative 1, negative 2, negative 3, negative 4. Okay, so I'm going to put a few values in here, and I'll explain after I do that. Okay, so I added a few symbols and numbers to this table. All that these red minuses mean is that if 1, 2, 3, and 4 are negative, then the following values are true for the coefficients of g of x. Because f of x is even, it doesn't change anything. But because g of x is odd, we're going to get opposite signs there. The other thing is that with odd functions, they have origin symmetry. Therefore, g of 0 will equal 0. Okay, so let's evaluate the following, for example, 8 and 9. So f of negative 2, what we know is that f of negative 2 is the same as f of positive 2. So f of negative 2 is actually 3. And g of 3 is positive 4. Okay, let's look at f of g of 0 plus 2. Well, we know that g of 0 equals 0, right? Because odd functions have to go through the origin. Okay, therefore, f of 0 plus 2 is the same as f of 2, which is equal to 3. All right, so that's it for this lesson. We'll see you next time, folks. Have a great day.